Hello and welcome back to CS420, a course on game hacking. In this lecture, we'll be covering base systems. Base systems are just ways to express numbers. The numbers on this slide are all the same number, written in different base systems, binary, decimal, and hex. Now, we dabbled in binary a little bit last lecture, but now we're going to develop a true understanding of how binary and hex work. Now, I know what you're thinking. I came here to learn how to hack, and now you're going to lecture me on numbers? Is this some sort of sick joke? The answer is yes, it is a sick joke, but don't blame me, I'm just the messenger. This is a small but necessary detour before we get back into hacking. This happens a lot when you want to learn cool subjects. If you want to learn machine learning, you need to learn a little bit of statistics. If you want to learn physics, you need to learn a little bit of calculus. We actually have it quite easy in comparison, we're just learning how to count again. Before we get started, let me give you some inspiration. This is an excerpt from a book about dead languages. Not programming languages, but actual spoken languages. It reads, "The Poppin language Bookieip has two different counting systems, one base 4 and another base 3. According to Bookieip custom, which system you use depends on which objects you are counting." So ancient Papua New Guineans actually knew two base systems. If a peasant living on a remote island several thousand years ago can learn multiple base systems, then an aspiring 21st century hacker with access to the world's knowledge and internet has no excuse. Let's actually take a look at this language. There's a few lessons it can teach us that we can apply to binary and hex. So on the left, we have objects that we count by 4s, things like coconuts, lizards, bows and arrows. And on the right, we have things that we count by 3s, things like beetle nuts, bananas, and shields. Now, I want to point something very interesting out. On the left, we have small yams, and on the right, we have big yams. That means if I wanted to sell you two groups of yams, you better be careful, because if I'm talking about small yams, then there's 8 of them. But if I'm talking about big yams, then that means there are 6 of them. The important lesson here is that numbers can mean different things depending on the context, depending on the base system. And just a side note, if you read up on this language, you'll find that I simplified things a little bit. It's quite fascinating, but really beyond the scope of this lecture to go into more detail. You can look it up on your own if you want. But let's take this lesson and apply it to what we know, our systems. If we have the number 10, we know what that is and we can visualize it. It's the number of fingers on our hands. Now, if we take that same number written down and look at it in the context of hexadecimal, well, it actually means 16. In binary, it actually means 2. It's similar to the problem I mentioned before with the yams. We need to know if it's big yams or little yams. We need to know if it's binary or hex. To avoid confusion, sometimes people put a 0x before a hex number and 0b before binary numbers. People don't always use these prefixes, so it can get a little confusing, but just know that when you see these prefixes, you can no longer trust your eyes and brain. The numbers are in those contexts now. Before we go on, let's take a step back and ask ourselves why we even need to learn this stuff. It goes without saying that humans use base 10. A common question people have is there anything special about base 10? And the answer is not really. We just chose it because it works well with the number of fingers we have. A lot of mathematicians actually think base 10 was a mistake. If you buy donuts in the USA, they come in 12, and there's a reason for that. 12 is easier to split with your friends. If there's 2 of you, you both get 6. If there's 3 of you, y'all get 4. If there's 4 of you, y'all get 3. And if there's 6 of you, everyone gets 2. It divides up really well. In math, that's known as a highly composite number. Now let's take a look at computers. They store information in either an on or off state, and this gives rise to a natural base 2 system. 0 for off, 1 for on. That's 2 options, base 2. Now this sucks for us as humans because we never learned base 2. We invented machines that do math in a system that the majority of us don't understand, so now we need to learn it. If you've been super observant, you may be asking, hey, what about hex? Where does that come from? Hex is base 16, how does that fit into this? I hinted at this earlier with my rant about the donuts. Different base systems are good for different problems. Base 2 is good because it can represent things that are on and off. Base 10 is good because that's how many fingers we have and it's convenient for humans. Base 12 is good for dividing things up. And you actually know another base, you just don't know that you know it. That's base 1. Base 1 is tally marks. Tally marks are good for counting things as they happen, like counting votes in a classroom or keeping track of how many times different teams have won in a competition. This is useful because you never have to erase, you can just keep adding more marks. Base 16 also solves a problem, but it's a subtle problem and a bit more nuanced. So we'll need to learn a few more things before we can get into it. Before we try to learn binary and hex, we need to unlearn decimal. This is the hardest part for people because you've been staring at decimal numbers your entire life. Let's pay close attention to how we count numbers. Once we get to 10, we recycle digits. The number 10 reuses the digits 1 and 0. The number 11 reuses 1 and 1 again. So let me ask you, why not invent a new symbol instead of just recycling? Right? What if we just kept going? In this example, A is 10, and B is 11, and so on. Well, obviously we can't come up with a new symbol for every number because there are infinite numbers, and it's just not sustainable. At some point, we need to reuse symbols, and base systems tell us how many digits we can use before we need to start recycling. Here's a system with way too many symbols. This is the Babylonian numeral system, and it's base 60. Maybe this is why the Babylonian Empire fell apart. I can just imagine a general trying to scribble down a note asking for the king to send 100 horses. Was it triangle, triangle, arrow, arrow, or arrow, arrow, triangle, triangle? It's like punching in a Konami code every time you want to ask for a simple favor. But it does have one thing going for it. It's base 60. It divides up very well, similar to 12. But it's still way too many symbols to memorize. But look what happens when we have too few digits. The Babylonians had too many, and it was overwhelming. With binary, we have too few, and it's even more unreadable. It turns out that there's a range of digits that work really well for humans, probably between 7 and 20. This is my own personal estimate. A linguist would be more suited to come up with an exact range, but you get the general idea. Let's do another thought experiment. What would happen if we invented a new digit? Let's add a new digit between 9 and 10 using the letter A. Well, the numbers get shifted now. A represents 10, which means that 10 actually represents 11. And if that's confusing, just count out the numbers on the bottom row. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The further we go, the worse the shifting gets. What we thought of as 10 actually represents 11, and what we used to think of as 20 actually represents 22. We can no longer trust our eyes. Here's another brain bender. What if we removed the number 9? Well, 10 would take its spot, so what we used to think of as 10 would actually now represent 9. What we used to think of as 20 would actually represent 18. The numbers are just shifted again, but this time in the opposite direction. Let's apply this to the systems that we need to learn. These are the numbers for each base system. Decimal is obviously 0 to 9 for a total of 10 choices, hence base 10. Binary is 0 and 1, totaling 2 choices. But hex needs 16 symbols, and that's 6 more than we used to because we're going from 10 to 16. So we need 6 new single-digit characters, so we just steal them from the alphabet. If we count these out similar to the previous thought experiments, the shifting gets really bad. A is 10, B is 11, C is 12, and so on. What we think of as 10 to us is actually 16. What we think of as 20 is actually 32. Now let's take a look at the same number represented in all 3 base systems. So all 3 of these numbers are the same. Notice how ugly the number is for decimal. And with hex and binary, there seems to be some sort of structure, right? It's a repeated letter. Well, I want to point something special out. Look what happens when we space out the binary and hex. For every 4 binary numbers, there's 1 hex number. If we change the hex number to be FA, FFF, and so on, look what happens to the binary. The group that used to be 1111 is actually now 1010. There's a strong correlation between the hex number and the corresponding 4 binary numbers. So this is what I was talking about earlier when I said that hex solves a problem. Humans can't read binary very well. It doesn't convert to decimal very well either. However, it is easy to convert from binary to hex. If you gave me 10,000 digits of binary, I could convert them to hex by hand by simply breaking them up into chunks of 4 and converting those 4-digit chunks into hex. If you ask someone to convert the same 10,000 digits of binary into decimal, no human could do it without a calculator. So now let's actually learn how to count in binary. I'll explain the same concept in a few different ways, so if one explanation doesn't make sense to you, don't worry. First, let's look at an idea that we're familiar with in decimal. If we have the number 99999 and we add 1, something happens. There's a cascade effect where all the 9s turn into 0s and we add a 1 to the very end. Well, in binary, it's the same idea. What would happen if we added 1 to this number? Well, there's a cascade effect where all the preceding 1s turn into 0s and we put a 1 at the end. But remember that in decimal, we run out of digits at 9, and in binary, we run out of digits at 1. So this cascading effect happens a lot more frequently. Let's take a look at binary counting in action. I'll just let the animation play out, and you can watch and try to figure out what's going on your own. There isn't too much I can really add here. Unfortunately, it's one of those things that either clicks or it doesn't. If not, we'll go over a few ways to think about this, and hopefully one of those other methods will click if this one isn't doing it for you. So let's take a look at another idea that we understand in decimal. We know that 100 is 10 times more powerful than 10, and we know that 1000 is 10 times more powerful than 100. So one way to think about this is that a 1 in the hundreds place is 10 times more powerful than a 1 in the tens place, and so on. Let's look at that same idea in binary. So the left column here is the binary number, and the right column is the corresponding decimal number. Now the top left number here, which is 1, we can ignore the leading zeros. It's the same thing as putting like a 0 before a decimal number. It doesn't matter, but a lot of people do it in binary to make it look cleaner. Okay, so now let's look at the next number. We know the top one is 1. Well, the next one is 2. And you can think of this as a 1 in the second position there is worth twice as much as a 1 in the first position, right? Similar to how in decimal, 100 is 10 times more powerful than 10. In this case, we're doing twice as powerful because we're base 2. So we have a 1 in the first position over here, and a 1 in the second position is twice as powerful, so it goes from 1 to 2. And now if we move that 1 over to the third position here, it's twice as powerful as the previous number, so this one is actually 4. So, a thought experiment. What do you think the number on the right represents? Well, it's actually pretty easy to do. You just add up how powerful each digit is. We established that 1 0 is worth 2, and that 1 0 0 is worth 4, so you can actually just add 2 and 4, and this number is 6. Let's take a look at the same idea in chart form. So the first row, we have 1 1 0 1 1, and we spread out those digits over the column. So we have 1 1 0 1 1. Now, we established that a 1 in the first position is only worth 1, but a 1 in the second position is worth 2, and so on. So if you look at the top rows here, or top column, sorry, we have 1, 2, 4, 8, 16, because each place is worth twice the previous. So what we can do is if the 1 is set, we add what it's worth. So 1 in the first position is worth 1, so we have 1 plus, we have a 1 in the second position, that's worth 2, so 1 plus 2. And this one's not set, so we don't do anything. There's a 0 here, we ignore it. Now there's an 8 set here, so 1 plus 2 plus 8, and there's a 1 in the 16 column. So now we have 1 plus 2 plus 8 plus 16. That gives us 27 in decimal. So now you know how to piece this together just by looking at it. Now let's look at the second row. This one's a little easier. There's a lot of zeros. The 1 bit is set, so we have 1 plus 2 isn't set, it's a 0, so we skip that 1. And the 4 bit is set, so 1 plus 4 for a total of 5. And if you want to do this last one, I'll leave that as an exercise to the reader, but it should work exactly the same way, very straightforward. And if we wanted to keep going, we would actually add rows for 32, then 64, then 128. I hope that makes some sense to you. I'm not gonna go through examples here, but the idea is that each position you multiply by 2, so the more digits you have, the more powerful the leftmost digits are. This is a neat trick. It's not super useful, but I thought I'd teach it anyways. You can actually count to 31 on one hand by treating your fingers as either 0 or 1. If you use both hands, you can actually count up to 1,023. It's just a little awkward because you can end up accidentally flipping people off when you count to 4, but it's still pretty neat. Just be sure not to insult your teachers if you show them this trick. And if it doesn't make much sense, you can just use a calculator. Let's actually jump into what that would look like. So here we have the Windows calculator. What we can do is go into the options here, switch to programmer mode, and this gives us access to conversions. So if we type in a number in decimals, say 255, we can click on the hex version here, and we can see that it's FF in hex. We can click on binary here to see that it's 1111 whatever in binary. And we can do this for any number. Just type in some giant number, we can see what it is in binary. We can also do it the other way. If we know what the number is in hex, we can click on hex, clear this, and then just start typing the hex number, and we can see what it is in binary. So this is wonderful. I taught you everything else for no reason, because it turns out that you'll probably just end up using this for most of everything you need to do. There's no reason to convert anything in your head these days. However, it's still very important to be able to eyeball small binary numbers and convert small numbers in your head. But if you're running into something like this, just use a calculator. Save yourself the time. If you're on Linux or Mac, they also have a programmer mode on their calculator. I'm not going to go over how to open that programmer mode on those, but it works almost exactly the same way, so there's no reason to be redundant here. The best way to solidify what you've learned is to actually get out there and do some hands-on activities. So I'm going to point a few out. There's some video games that I'd like you to play. So the first game I wanted to point out is this Flippy Bit and the Attack of the Hexadecimals from base 16. It's a little bit of a cheesy game, but it's free and it really drives the relationship between binary and hex. So let's jump into this. So the trick here is to match the first 4 binary numbers with the first hex digit, and the last 4 with the last hex digit. You can see the number down here as I type it out. So here we want to make a 7 using these first 4, and a 4, which is going to be this bit. FF is super easy. Every bit gets set. Here we want E, here we want a 7, and at some point you can do this without really thinking, right? It's not too bad. It looks overwhelming, and that's kind of the whole point of it, is it's not overwhelming, and once you get into it, you can convert the stuff in your head. So the next game I wanted to point out is Squalr. There's a mini game in Squalr that drills in binary, decimal, and hex through gameplay. So here we have blue cards that are binary, green cards that are hex, and white cards that are decimal. And to learn how they work through standard gameplay, he just made my card weaker, and that's all there is to it. And of course, links to both of these will be in the description. So last time we left off with this as our understanding of what a computer program was, but now let's update it. So before, we know that there's groups of 8 bits, they can be addressed, so the first group is 0, the next group is 1, and so on. To represent larger numbers, we can use more groups of bits. So at the top here, we have this giant group of eight groups of 8 bits, which represents that giant 7995 number. And then there's smaller groups, right? This group of 1 that represents the value 101 at address 169. So let's take this idea, and now we're going to replace those with hex numbers. So hex can be used to represent binary numbers, and it's a little more human readable. So we'll almost never look at binary again. We'll probably always be using hex, except for a few exceptions in the future. What used to be groups of 8 binary digits are now represented by 2 hex digits. And I'll point a few examples out to make sure that this is clear. So the group of numbers with the value 623 is using 32 bits of information, or 4 bytes. And the yellow group of numbers is using 16 bits of information, or 2 bytes. And if it's still confusing, I recommend comparing it with the previous screenshot. Anyhow, I hope you learned something about how binary numbers and hex work. And as usual, if you need anything clarified or have any feedback, drop a comment below. Thank you.